So I think there's another level that you can add to the Encyclopedia Inflationaris, which is, to use your own words, the naturalness of a model. And we have to be careful because naturalness means many things. But so, it would be work, but you would have to look at it model by model and see, does this model make sense according to a number of guiding principles? Effective field theory, causality. That you could just sit down and you could sit down and make a list of things and then just check it and come up with some quantifier. What do you think?
I think it would be great, but I think it's technically speaking, it's quite hard to do. In fact, I don't know exactly how to do it at the technical level. When you look at given models of inflation, you immediately feel whether this is a model that is appealing or not, because some of them are really based on high energy physics consideration, others are just ad hoc models. So when you look at them, you immediately feel whether a model looks better than another, but to come up with something which is at the quantitative level that would quantify this, I must confess, this is not so clear to me. But I fully agree with you that it would be great to be able to design such an approach.
The reason I say this is, like you, it is a gut feeling. One looks at a theory and you think, oh, that's not very good. Oh, this. But I think sometimes this gut feeling can be a bit misguided. More in the sense of looking at theories and thinking, oh, this is acceptable, when it's actually not acceptable. Let me talk about a particular example. In your analysis, in your encyclopedia, there is one model that stands head and shoulders above all the others, which is the Starobinsky model of inflation. And this is a model where you assume that there are higher order corrections to the gravitational action. And what I mean by that, normally the gravitational action depends on something known as the Ricci curvature, the curvature of space-time. And the Starobinsky model also depends on the square of the Ricci curvature. So you add this extra term. And people often say, this is what you expect from quantum gravity. This is what you expect from higher order corrections. And so people think it's natural. But in fact, it's pretty unnatural, because you not only expect, if you assume those higher order corrections, there are all these other higher order corrections that come in at the same level, which will completely change the dynamics. So in fact, Starobinsky model is a very unnatural theory from fundamental physics point of view. And it's things like that I think would really filter away models. And you might find that the models that fit the data really well are completely unnatural physically, and so we shouldn't even be looking at them. So I think I agree with you that coming up with a precise quantifier might be difficult, but you might just come up with a gross selection, broad selection, which might already change the landscape of the analysis.
But yeah, I think this Bayesian analysis will never tell you this. The Bayesian analysis tells you if you want to fit well the data with a simple model, then you need the Starobinsky. You need a potential which is the one predicted by the Starobinsky model. Maybe I can also add some comments about the Starobinsky model itself. So I agree with you that you have higher order corrections when you see the Starobinsky model as R plus R squared and so on. But this is not the only way to see the Starobinsky models. For instance, you can also see the Starobinsky model as a model of inflation where the inflaton field is the Higgs boson. And you can even argue that, so you take the standard model and you add only one term to the standard model, which is a non-minimal coupling between gravity and the Higgs boson. And in some sense, by magic, you immediately produce the potential of the Starobinsky model. So, and there are other models that are known as alpha attractors, that are quite fashionable at the moment, that produces something which is also similar to the Starobinsky model, also it's not exactly the same. But it produces something which is important to fit the data, namely that you have a flat plateau in the potentials. So I would not be so negative about the physical motivation for the Starobinsky model, because I think there are various ways to look at this model.
So two things. First of all, even those alternative views of the Starobinsky model have their own problems. And you can already see in the Higgs inflation problem that you have a very large coupling. And so you have to include you might have to include other things as well. But what I was going to say is I think you are being less ambitious than you could be with the Bayesian approach. It's all about priors. And it's all about what prior you give to a model. And I do believe that there should be a way of adding another level of priors into your analysis. And
so I can tell you something. When we wrote this paper, we wanted to compute the Bayesian evidence of all the models. And then what we wanted to do is to write a second volume. And what we wanted to do is to try to calculate the Bayesian evidence of categories of models. So we started to classify the models in the following way. So we had the models, for instance, that come from string theory, models that come from supersymmetry. And what we wanted to do is to give a Bayesian evidence to these categories of models. So the Bayesian evidence, technically, the Bayesian evidence would have been a weighted sum of the Bayesian evidence of the models in each category. But then, soon, we started to realize that a model can belong to many different categories, because it has, sometimes you come up with the same potential, but from different origins. And so we gave up because there was no clear way to calculate the Bayesian evidence of those categories of models. And so this is a concrete example of the difficulty that you face if you want to realize your idea. But maybe there are other ways.
I believe I'm just, not having done it, I can say whatever I want.